Hello there, and welcome to Get Sleepy Science. I'm so glad you found your way here tonight. The universe contains objects so mysterious, so powerful, that they challenge everything we think we know about space and time. Tonight, we'll drift gently through the cosmos, exploring the strange and beautiful truths about black holes. Those cosmic enigmas where gravity becomes so intense that not even light can escape. These are places where the laws of physics are stretched to their very limits, and where some of the universe's deepest mysteries still wait to be understood. Wherever you are right now, perhaps with the windows closed against the night, or with the gentle darkness settling around you, allow yourself to settle into this shared moment of stillness. Tonight, explore 100 remarkable truths about black holes. From the supermassive giants lurking at the centers of galaxies, to the stellar remnants scattered throughout space, to the theoretical mysteries that physicists are only beginning to understand. We'll journey to the edge of what is known, where science meets wonder, and where curiosity becomes a gentle companion for sleep. If this quiet exploration of the cosmos helps you unwind, a gentle like and subscribe helps other stargazers find their way here too. It only takes a moment, but it means the universe to us, one sleepy soul at a time. For now, you don't need to do anything at all. Just let your shoulders soften. Let your breathing fall into its own rhythm. Imagine yourself drifting in a space of gentle curiosity, where facts become stories and stories become dreams. The mysteries of black holes have puzzled humanity for generations, but tonight, they're simply here to keep you company as you rest. Now, if you're ready, let's begin our quiet journey into darkness and light. Now, if you'd like, close your eyes and take a deep breath. Imagine you're lying in a small spacecraft, drifting gently through the endless night sky, moving without boundaries, without destination, only the light of distant stars and absolute silence. Let go of all limits. Let your mind drift through infinite space. And when you're ready, begin. A black hole is a region of space-time where gravity is so strong that nothing, not even light, can escape from it. The boundary surrounding this region is called the event horizon, named because once you cross it, no events or information from inside can ever reach the outside universe again. Black holes form when massive stars collapse at the end of their lives, or when enormous amounts of matter accumulate in one place. What makes them truly mysterious is that the normal rules of physics we rely on seem to break down at their centers. Inside a black hole lies something called a singularity, a point where density becomes infinite, and our current understanding of space and time simply stops working. Scientists have been studying black holes for over a century, yet they continue to reveal new surprises with each observation. The term black hole was coined by physicist John Wheeler in 1967, though the concept itself dates back much further. In 1796, a scientist named John Michel theorized about dark stars so massive that light couldn't escape them. Later, when Albert Einstein published his theory of general relativity in 1915, it provided the mathematical framework that predicted these objects could actually exist. Einstein himself didn't believe black holes were real. He thought they were just mathematical curiosities. For decades, most physicists agreed with him, thinking nature would never actually create something so extreme. It wasn't until the middle of the 20th century when scientists began detecting strange X-ray signals from space, that the evidence for real black holes became overwhelming. Sometimes, our universe is stranger than even our greatest minds can imagine. Black holes come in different sizes, and astronomers classify them into several categories. Stellar black holes form from the collapse of individual massive stars and typically have masses between 3 and several dozen times that of our Sun. Intermediate mass black holes, which scientists are still studying, fall somewhere in between, with masses from hundreds to thousands of solar masses. Supermassive black holes, found at the centers of most galaxies, contain millions or even billions of times the mass of the Sun. Our own Milky Way galaxy has a supermassive black hole at its center called Sagittarius A star, which weighs about 4 million solar masses. Scientists have also proposed the existence of primordial black holes, which would have formed in the earliest moments after the Big Bang from extremely dense pockets of matter. Each type tells us something different about how the universe works. When a massive star runs out of fuel, it can no longer support itself against its own gravity. The star's core suddenly collapses in a fraction of a second, creating a supernova explosion that can briefly outshine an entire galaxy. If the remaining core is massive enough, more than about 3 times the mass of our Sun, nothing in the universe can stop it from collapsing into a black hole. The matter compresses down and down, becoming denser than anything in normal experience. Imagine squeezing the entire Earth down to the size of a marble, that still wouldn't be as dense as a black hole. The collapse continues until all the mass concentrates at a single point called a singularity. Around this singularity, the event horizon forms, marking the point of no return. This entire process, from collapse to black hole formation, happens remarkably quickly, faster than you can blink. The event horizon isn't a physical surface you could touch. It's simply the boundary where escape velocity equals the speed of light. As noted in recent research from November 2025, this is a subjective reflection. Nothing we know of can travel faster than light, so once something crosses this boundary, it can never come back out. The size of the event horizon depends on the black hole's mass. For a stellar black hole with 10 solar masses, the event horizon would be about 60 kilometers in diameter, roughly the width of a small city. For Sagittarius A star, the supermassive black hole at our galaxy's center, the event horizon is about 24 million kilometers in diameter, large enough to fit several planets from our solar system inside. Interestingly, if you were falling toward a black hole, you wouldn't notice anything special as you crossed the event horizon. From your perspective, it would seem like empty space, with no wall or barrier marking where you passed the point of no return. The gravitational pull near a black hole creates something called tidal forces, which would affect anything falling toward it. This effect is sometimes called spaghettification, a curious phenomenon where gravity varies with distance. The closer side of anything falling would feel slightly stronger pull than the farther side, creating a gentle stretch. For stellar black holes, this happens gradually as you approach. It's like being in a place where up and down have different meanings, where space itself stretches in quiet, invisible ways. Interestingly, with supermassive black holes, the event horizon is so far from the center that tidal forces at the horizon itself are relatively gentle. You could theoretically cross the event horizon of a supermassive black hole and survive for a brief time before the increasing gravity deep inside eventually became too strong. It's a reminder that size matters, even in the most extreme environments. Time behaves strangely near black holes due to gravitational time dilation, an effect predicted by Einstein's relativity and confirmed through numerous experiments. The stronger the gravitational field, the more slowly time passes relative to observers far away. If you could watch someone falling toward a black hole from a safe distance, you would see them appear to slow down as they approached the event horizon. Their movements would become more and more sluggish, and the light from them would become increasingly redshifted, shifting toward longer, redder wavelengths. They would never quite seem to reach the horizon, appearing frozen at the edge for all eternity. However, from the falling person's perspective, time would feel completely normal. They would cross the event horizon in a finite amount of their own time, unaware that to the outside universe, they appear frozen forever. This strange disconnect shows how deeply gravity affects not just space, but time itself. Black holes are not cosmic vacuum cleaners that suck up everything around them. This is perhaps the most common misconception about them. At a distance, a black hole's gravity behaves just like the gravity of any other object with the same mass. If our sun suddenly turned into a black hole, which it won't, because it's not massive enough, the Earth would continue orbiting exactly as it does now. We wouldn't be pulled into the black hole or experience any change in our orbit. The extreme effects only occur very close to the event horizon itself. Planets, stars, and even light can orbit a black hole safely, as long as they maintain enough distance. Many black holes exist quietly in space, not consuming anything, simply warping space-time around them. They're dangerous only if you get too close, just as the sun would be dangerous if Earth moved too close to it. In April 2019, humanity saw the first direct image of a black hole, captured by the Event Horizon Telescope collaboration. The image showed the supermassive black hole at the center of galaxy Messier 87, located 55 million light-years away. What we saw wasn't the black hole itself. Remember, black holes don't emit light, but rather a bright ring of glowing matter swirling around it. This ring appears because the intense gravity bends light from the hot gas orbiting the black hole, creating what's called a photon sphere. The dark center, larger than the event horizon itself, is called the black hole's shadow. This shadow appears because gravity is bending all the light around and behind the black hole. The achievement required linking 8 radio telescopes across the planet to create a virtual telescope the size of Earth. It was like trying to photograph a bagel on the moon from here on Earth. 3 years later, in May 2022, the Event Horizon Telescope collaboration released a second historic image, this time of Sagittarius A star, the black hole at the center of our own Milky Way galaxy. Though Sagittarius A star is much closer to us than the M87 black hole, it was actually harder to photograph. The gas orbiting our galaxy's black hole moves very quickly, changing in just minutes, whereas M87's environment changes over days or weeks. Imagine trying to photograph a squirmy toddler versus a patient adult. Our galaxy's black hole is the squirmy toddler. The researchers had to take thousands of images and combine them to create the final picture. More recently, in March 2024, scientists released another image of Sagittarius A star, this time in polarized light, revealing the magnetic field structure spiraling around it. Each new image teaches us more about these mysterious objects at the hearts of galaxies. Most galaxies, including our Milky Way, have supermassive black holes at their centers, and there appears to be a deep connection between a galaxy and its central black hole. Astronomers have found that the mass of a galaxy's central black hole is closely related to properties of the galaxy itself, particularly the velocity of stars in the galaxy's central region. This relationship suggests that galaxies and their black holes grow together over cosmic time, influencing each other's development. A recent hypothesis proposes this happens through a process where the black holes, powerful jets, and radiation affect star formation throughout the galaxy. When a supermassive black hole actively feeds, it can release enormous amounts of energy that heat the surrounding gas, sometimes preventing new stars from forming. In this way, black holes may regulate the growth of their host galaxies, acting like cosmic thermostats. The details of this relationship remain an active area of research, with each new observation adding pieces to the puzzle. Quasars are among the brightest objects in the universe, and they're powered by supermassive black holes. A quasar forms when a supermassive black hole actively consumes enormous amounts of material, heating it to millions of degrees before it falls past the event horizon. This superheated material shines so brilliantly that a single quasar can outshine its entire host galaxy, containing hundreds of billions of stars. In February 2024, astronomers announced the discovery of the brightest quasar ever observed. This object, visible as it was about 12 billion years ago, is powered by a black hole, consuming the equivalent of one sun's worth of matter every single day. The black hole itself has a mass between 17 and 19 billion times that of our sun. Such discoveries help scientists understand how supermassive black holes grew so large so quickly in the early universe, a question that still puzzles astronomers today. In November 2024, astronomers announced the discovery of a black hole that's breaking records by eating faster than should be possible, designated LID 568. This supermassive black hole is consuming matter at more than 40 times the Eddington limit, the theoretical maximum feeding rate. The Eddington limit exists because when a black hole feeds very rapidly, the radiation from the super-hot infalling matter pushes outward, which should prevent more matter from falling in. It's like trying to eat while blowing air outward from your mouth. The air should push the food away. Yet LID 568 is somehow bypassing this limit, which scientists observe as a personal impression suggests might happen during brief, intense feeding episodes. This discovery, made using the James Webb Space Telescope and Chandra X-ray Observatory, may help explain how supermassive black holes grew to enormous sizes when the universe was still young. The black hole is seen as it was just 1.5 billion years after the Big Bang. Black holes can exist in binary systems, orbiting around each other in a cosmic dance. When two black holes orbit closely enough, they gradually spiral inward, releasing energy in the form of gravitational waves, ripples in the fabric of space-time itself. In October 2025, scientists reported the most remarkable direct visual evidence yet, the first ever image of two black holes orbiting each other. The image shows quasar OJ287, which contains two black holes circling one another. The larger black hole has about 18 billion solar masses, while its companion is about 150 million solar masses. They orbit each other every 12 years, with bright jets of particles marking their positions in the image captured by an international team of radio telescopes. This visual confirmation supports decades of predictions about how binary black holes behave and provides new insights into galaxy evolution, as most large galaxies likely merge their central black holes when they collide. When black holes finally spiral together and merge, they create gravitational waves that ripple across the universe. In September 2015, the Laser Interferometer Gravitational Wave Observatory, known as LIGO, made the first direct detection of gravitational waves from merging black holes. This discovery earned the Nobel Prize in Physics and opened an entirely new way of observing the universe. The signal, designated GW150914, came from two black holes that merged about 1.3 billion years ago. Each black hole was about 30 times the mass of the Sun, and when they merged, they created a new black hole of about 62 solar masses. The remaining energy, equivalent to 3 solar masses, was released as gravitational waves that stretched and squeezed space-time itself as they passed through Earth. In the years since, LIGO and its partner observatories have detected many more black hole mergers, including recent October and November 2024 detections showing unusual spin properties that suggest some black holes are second-generation objects, formed from previous mergers. Despite their name, black holes aren't actually completely black, at least according to theory. In 1974, Stephen Hawking proposed that black holes should emit a faint glow of radiation due to quantum effects near the event horizon. This Hawking radiation arises from the strange behavior of empty space, which isn't truly empty but filled with temporary particle-antiparticle pairs that pop in and out of existence near a black hole's event horizon. One particle from such a pair might fall into the black hole, while the other escapes, appearing as radiation. The temperature of this radiation is inversely proportional to the black hole's mass. Larger black holes are colder, smaller ones are hotter. For stellar mass and supermassive black holes, this radiation is incredibly faint, far too weak to detect with current technology. However, recent research in 2024 and 2025 has proposed new methods for detecting Hawking radiation from smaller, primordial black holes or from black hole morsels created during black hole mergers. If confirmed, it would be one of the most important discoveries in physics, bridging quantum mechanics and relativity. And now, let's pause for just a moment. Take a deep breath and feel this. Every atom in your body, the carbon, the nitrogen, the oxygen, the iron, was created in the core of a dying star. The spacecraft we build, the astronomers who study black holes, the telescopes pointed at the sky, all made from the material of the universe, returning to the universe. Feel yourself carrying the trace of ancient stars. Every breath you take, you're breathing the same air that astronauts breathed while looking down at Earth from above. We are all space travelers, flying on a small planet through the galaxy. Now we continue. In April 2024, astronomers announced the discovery of Gaia BH3, the most massive stellar black hole ever found in the Milky Way, located about 1,926 light-years away in the constellation Aquila. This sleeping giant has a mass nearly 33 times that of our Sun. The European Space Agency's Gaia Space Telescope detected it through the wobble it creates in its companion star's motion. Most stellar black holes in our galaxy average about 10 solar masses, making Gaia BH3 truly exceptional. Scientists believe such massive stellar black holes form from stars that are metal-poor, containing mostly hydrogen and helium, which lose less mass during their lifetimes and have more material left over to collapse into a black hole. This discovery, along with Gaia BH1 discovered earlier, suggests there may be many more massive black holes quietly hiding in our galaxy, waiting to be found through their gravitational effects on nearby stars. The Event Horizon Telescope continues to push the boundaries of what we can observe. In August 2024, the collaboration announced they had achieved observations at 345 GHz, the highest resolution black hole observations ever obtained from Earth's surface. This is like upgrading from standard definition to high-definition television. The higher frequency allows astronomers to see details 50% sharper than previous images and will enable them to create color images by observing at multiple frequencies. These enhanced observations will help scientists better distinguish between the effects of gravity predicted by Einstein's theory and the behavior of hot gas and magnetic fields around black holes. The team is currently analyzing data from Sagittarius A star and M87 at these new frequencies. Observing at this higher frequency presented challenges because water vapor in Earth's atmosphere absorbs these signals more strongly, requiring perfect weather conditions simultaneously at multiple telescope sites around the world. Not all black holes stay at the centers of galaxies. In May 2025, researchers announced the discovery of two massive black holes actively feeding in the same galaxy, but one of them is located about 2,600 light-years away from the galaxy's core. This rogue black hole was discovered through a tidal disruption event, the signature of a star being torn apart and consumed. The galaxy in question is about 600 million light-years from Earth, and both black holes are consuming material right now. The wandering black hole has a mass about 100 million times that of our Sun. It likely originated from a smaller galaxy that merged with the larger one in the past. This discovery validates theoretical predictions that galaxy mergers should leave multiple massive black holes scattered throughout the merged galaxy. Over billions of years, these black holes will slowly spiral toward the center, eventually merging themselves in a spectacular release of gravitational waves. If you could somehow survive near a black hole, you would witness truly bizarre optical effects. Light from stars behind the black hole would be bent around it, creating multiple images of the same star in different positions. Some stars might appear as rings encircling the black hole. You might even see the back of your own head, as light from behind you curves around the black hole and returns to your eyes. The entire sky would appear distorted, compressed toward the black hole as if looking through a fisheye lens. Near the event horizon of a rapidly spinning black hole, space itself is dragged around in a phenomenon called frame dragging. If you tried to stand still, you would find yourself inevitably pulled along in the direction of the black hole's rotation, like standing on a moving walkway. These effects aren't science fiction. They're genuine predictions of Einstein's relativity, confirmed through astronomical observations. Black holes can spin, and their spin affects the space around them in fascinating ways. The M87 black hole, whose image made history, appears to spin rapidly, likely close to the maximum possible speed. perhaps around 90% of the cosmic speed limit for rotating black holes. When a black hole spins, it drags space-time along with it, creating a region called the ergosphere, just outside the event horizon. In the ergosphere, space itself is pulled around the black hole so strongly that nothing can remain stationary. Everything must move in the direction of the spin. The faster a black hole spins, the more energy can potentially be extracted from it through a process called the Penrose process, where particles split near the ergosphere and one half falls into the black hole, while the other escapes with more energy than it originally had. Some scientists speculate that advanced civilizations might someday use spinning black holes as enormous power sources, though we are many centuries away from such technology. The singularity at the center of a black hole is where our current understanding of physics completely breaks down. According to general relativity, all the mass of a black hole compresses down to a point of infinite density. But infinity appearing in physical equations usually signals that our theory is incomplete. Most physicists believe that quantum effects, which we don't yet fully understand at this extreme scale, would prevent a true infinity from forming. This represents the frontier of theoretical physics, where ideas remain to be tested. The singularity represents the boundary of our knowledge, a place where general relativity and quantum mechanics both apply but contradict each other. A complete theory of quantum gravity, which many physicists are working toward, might reveal what really happens at the center of a black hole. String theory, loop quantum gravity, and other approaches offer different possibilities, but we have no experimental way to test them yet. The singularity reminds us that for all we know, there are still deep mysteries waiting to be solved. Some black holes produce powerful jets of particles and energy that stream outward at nearly the speed of light, extending for thousands of light years into space. These jets are among the most energetic phenomena in the universe. In December 2024, the Event Horizon Telescope reported preparing to image the jets launching from the NGC 1052 galaxy, which has a supermassive black hole that produces two jets stretching thousands of light years outward. The jets appear to be powered by magnetic fields twisted around the spinning black hole, which accelerate particles to tremendous speeds. The M87 black hole also produces a prominent jet, visible in the first black hole image as enhanced brightness on one side of the ring. These jets can affect entire galaxies, heating gas that would otherwise form new stars. Understanding how black holes launch these jets is one of the major goals of modern astrophysics, connecting the smallest scales at the event horizon to the largest scales of galaxy evolution. In March 2024, astronomers observed strong and organized magnetic fields spiraling around Sagittarius, a star for the first time, using polarized light observations from the Event Horizon Telescope. Polarization reveals the direction of magnetic field lines. Much like polarized sunglasses reveal glare patterns on water, the magnetic field structure around our galaxy's black hole looks remarkably similar to that of M87. Despite M87 being more than 1,500 times more massive. This similarity hints at universal mechanisms governing how black holes interact with their environments. The magnetic fields appear strong enough to launch jets, leading scientists to speculate that Sagittarius A star might have a hidden jet that hasn't been detected yet. If confirmed, this would be exciting evidence that even relatively quiet black holes like ours maintain the magnetic infrastructure for dramatic activity. It might simply be that our black hole isn't actively feeding enough right now to produce a visible jet. Black holes can merge with other compact objects besides black holes. In recent years, gravitational wave detectors have observed mergers between black holes and neutron stars, the ultra-dense cores of collapsed stars that aren't quite massive enough to become black holes themselves. When a black hole and neutron star spiral together, the neutron star is gradually torn apart by tidal forces before being consumed. This produces gravitational waves with a distinctive pattern that allows scientists to identify the nature of the merging objects. These events may also produce bright electromagnetic signals if matter from the shredded neutron star is ejected during the merger. Such events are important for understanding how heavy elements like gold and platinum are created and distributed throughout the universe. Each merger detection adds to our understanding of the population of compact objects in the universe and how they interact. Intermediate mass black holes, with masses between 100 and 100,000 times that of the Sun, have been particularly elusive to find. They're too massive to form from single stellar collapses, but too small to be the supermassive black holes at galaxy centers. In May 2025, researchers reported new evidence for several intermediate mass black holes through different observational techniques. One possible formation mechanism suggests they form in dense star clusters, where stellar mass black holes merge repeatedly over time, growing progressively larger. Another possibility is that they're seeds left over from the early universe that never grew large enough to become supermassive. Finding and studying these intermediate mass black holes would fill in a crucial gap in our understanding of how supermassive black holes formed and grew to their current enormous sizes. Each candidate discovered brings us closer to solving this puzzle. Some stars have been observed orbiting so close to Sagittarius, a star that they complete a full orbit in just a few years. One star, designated S2, orbits our galaxy's black hole in only 16 years, traveling at speeds up to 3% the speed of light at its closest approach. Astronomers have tracked S2 and other stars in this S-star cluster for over 2 decades, and their orbits provide some of the strongest evidence that Sagittarius A star really is a supermassive black hole, rather than some other type of object. The extreme speeds and tight orbits of these stars also provide opportunities to test general relativity in the strong gravitational field close to a massive object. Measurements of S2's orbit have confirmed predictions about how light should be affected by gravity and how orbits should precess in strong gravitational fields. These stars are living laboratories for testing our understanding of gravity and space-time. If you're still here, still awake, still drifting with us through these stories, take a slow breath. Notice how your body feels a little lighter now, as if gravity itself has loosened its grip just slightly. We're traveling through space together, you and I, and everyone listening in the quiet dark, floating through facts like asteroids drifting through the void. There's no rush, no destination, just the gentle momentum of curiosity carrying us forward. Let's continue. The shadow of a black hole, that dark center we see in images, is actually larger than the event horizon itself. Light traveling near a black hole follows curved paths, and at a certain distance called the photon sphere, light can actually orbit the black hole in circles. This creates a dark region about 2.5 times wider than the event horizon, which is what we see as the black hole's shadow. Any light that passes inside this photon sphere will either spiral into the black hole or orbit it chaotically. The size and shape of this shadow encode information about the black hole's mass and spin. By measuring the shadow precisely, astronomers can test whether black holes really behave as Einstein's relativity predicts. So far, observations match the predictions beautifully, but scientists remain vigilant for any deviations that might hint at new physics beyond our current theories. Black holes create regions where the usual sequence of cause and effect becomes ambiguous. Events that appear simultaneous to a distant observer might happen at distinctly different moments for someone nearby. Two people, comparing notes after one, stayed far away while the other approached closer, would find that their experiences of when things happened no longer match. This isn't just about watches running at different speeds. It's about the fundamental ordering of events becoming observer-dependent near extreme gravity. The concepts of before and after that seem absolute in everyday life, become flexible near a black hole. This profound warping of causality has been measured with precise atomic clocks at different elevations on Earth, confirming that time genuinely passes at different rates in different gravitational fields. Near a black hole, these effects become extreme. Some theoretical physicists have proposed that black holes might connect to other regions of spacetime through structures called wormholes. If wormholes exist, they might theoretically allow travel between distant parts of the universe, or even between different universes entirely. However, most physicists believe that even if wormholes could exist, they would be incredibly unstable and would collapse immediately unless supported by exotic forms of matter with negative energy, something we've never observed, and that might not exist. The mathematics of general relativity permits wormhole solutions, but mathematics alone doesn't guarantee physical reality. It's important to note that this remains highly speculative, more in the realm of mathematical curiosity than observational science. Still, exploring these possibilities helps physicists understand the limits and implications of our theories. The information paradox is one of the deepest puzzles about black holes. When anything falls into a black hole, it seems like all information about that object's quantum state is lost forever, swallowed by the singularity. But quantum mechanics insists that information cannot be truly destroyed. It must be preserved somehow. This creates an apparent contradiction between quantum mechanics and general relativity. Stephen Hawking wrestled with this paradox for decades and eventually proposed that information might escape through subtle correlations in Hawking radiation over extremely long timescales. Recent theoretical work suggests the information might be encoded on the event horizon itself, like a hologram, or might escape during the black hole's final moments of evaporation. The paradox remains unsolved, representing one of the key challenges in developing a complete theory of quantum gravity. When a supermassive black hole suddenly starts consuming large amounts of matter, it's said to wake up. In August 2025, astronomers reported observing this rare phenomenon in a previously dormant black hole. The galaxy in question had appeared quiet for years, but suddenly began brightening dramatically as its central black hole started feeding on gas and dust that wandered too close. Such awakenings can last for thousands of years, or might be brief episodes lasting only decades. Scientists don't fully understand what triggers these feeding episodes. Sometimes It might be a star that ventures too close and gets disrupted, sending debris spiraling into the black hole. Other times, gas from galaxy mergers might funnel toward the center. Watching a black hole wake up helps astronomers understand the cycles of activity and quiescence that these objects experience over cosmic time. Black holes can disrupt stars through tidal forces long before consuming them. When a star passes close enough to a black hole, the difference in gravitational pull between the near and far sides of the star can overcome the star's own gravity, holding it together. The star gradually stretches and comes apart in what's called a tidal disruption event, a slow unraveling rather than sudden violence. About half the star's material typically falls toward the black hole, creating a bright flare of radiation as it heats up. The other half is flung outward into space. The Zwicky Transient Facility has discovered nearly 100 such events since 2018, almost all of them at the centers of galaxies. These events produce characteristic signatures in light that allow astronomers to distinguish them from other cosmic phenomena. Each tidal disruption event teaches us about both the black hole and the ill-fated star. The immense gravity of a black hole creates a phenomenon called gravitational lensing, where the black hole acts like a magnifying glass for light passing nearby. Light from distant galaxies can be bent around a black hole, creating multiple images or distorted arcs of the same background object. In some cases, the alignment is so perfect that light is bent into a complete ring around the black hole, called an Einstein ring. Astronomers use gravitational lensing as a tool to study both the black holes doing the lensing and the distant galaxies being magnified. One recent study discovered what might be one of the most massive black holes ever found, weighing about 36 billion solar masses. By analyzing the Einstein ring, it created around a distant galaxy. These cosmic alignments turn black holes into natural telescopes, allowing us to see objects that would otherwise be too faint to detect. Not all objects that orbit close to black holes are doomed to fall in. Some stars have been found in incredibly tight orbits that they've maintained for many orbital periods, surviving where less fortunate stars have been destroyed. One star system, designated V404 Cygni, was observed returning for a second helping at a black hole, the first confirmed case of a star surviving one close encounter and coming back for another. The star is in an elliptical orbit that brings it close to the black hole periodically. Each close pass strips away some of the star's outer layers, feeding the black hole while the star's core survives. This repeated feeding process might be more common than once thought, as stars in certain orbits can survive multiple encounters if their cores remain intact. These survivors provide opportunities to study the gradual process of stellar disruption in slow motion. In December 2024, scientists using multiple telescope networks, including the Event Horizon Telescope, observed M87's black hole and its jet during a rare gamma-ray flaring episode. This was the first very high-energy flare recorded from M87 since 2010. The simultaneous observations across different wavelengths of light, from radio waves to gamma rays, provided unprecedented data about the connection between the black hole's accretion disk and its powerful jet. The flare lasted several days and revealed rapid changes in the jet's structure. These observations suggest that instabilities in the accretion disk can trigger bursts of activity that propagate outward along the jet at nearly the speed of light. Understanding these flares helps scientists piece together the complex relationships between black holes, the material swirling around them, and the enormous jets they launch into space. The study of black holes has evolved from theoretical speculation to detailed observation in less than a century. From Einstein's equations predicting their existence to the first indirect evidence from X-ray astronomy, to gravitational wave detection, to finally imaging them directly, each technological advance has revealed new layers of complexity. Current and future missions will continue this exploration. The Laser Interferometer Space Antenna, or LISA, scheduled for launch in the 2030s, will detect gravitational waves from supermassive black hole mergers across the universe. The Next Generation Event Horizon Telescope plans to add more telescopes and observe at additional frequencies, potentially creating movies of matter swirling around black holes in real time. Each new window we open on the universe brings fresh surprises and deeper mysteries, reminding us how much remains to be learned. We've traveled halfway, and in this moment, let each breath guide you to realize, time is yours, a separate stream that only you are living. While the vast universe continues to spin, expand, change, this second you're breathing, listening, is unique. Cherish the present moment, knowing that right now, your time is unique in the universe. And we continue drifting. Theoretical physicists have explored what might happen inside a black hole's event horizon. Different models suggest different possibilities. Some predict that anyone crossing the horizon would experience a wall of intense radiation, a firewall that would incinerate them instantly. Others suggest the crossing would be smooth and uneventful, at least initially. Still others propose that the interior might be connected to other universes or other regions of space-time. Because nothing can send information back from inside the event horizon, we may never know for certain what happens there through direct observation. The interior of a black hole represents perhaps the ultimate unknown in physics, a region forever hidden from external view. Science thrives on mysteries like this, which push theories to their limits. Black holes can exist in surprising places. Besides the supermassive ones at galaxy centers and stellar mass ones scattered throughout galaxies, scientists search for primordial black holes that might have formed shortly after the Big Bang. These could have a wide range of masses, from smaller than an atom to thousands of times the mass of the Sun. If they exist, they might make up some or all of the mysterious dark matter that we know exists but cannot see. In June 2025, researchers proposed new ways to detect primordial black holes by looking for the Hawking radiation they might emit as they pass through our solar system. Simulations suggest about one detectable event per year might be possible with current instruments. These tiny black holes remain hypothetical, but detecting even one would revolutionize our understanding of the early universe. The Event Horizon Telescope operates through a technique called Very Long Baseline Interferometry. Multiple radio telescopes around the world observe the same target simultaneously. The data from each telescope is recorded with atomic clock precision. Then the hard drives are physically shipped to central locations where supercomputers combine the signals. This creates a virtual telescope with a diameter equal to the maximum distance between telescopes, essentially the size of Earth. The resolution depends on the baseline length divided by the wavelength observed. This is why adding distant telescopes and observing at shorter wavelengths both improve the images. Sites in Antarctica, Chile, Hawaii, Europe, and elsewhere work together, requiring clear weather at all locations simultaneously. It's a remarkable example of international scientific cooperation. Some black holes appear to exist in unexpected isolation, far from any visible star or gas that might feed them. These are called rogue, or wandering black holes, likely ejected from their birth locations by gravitational interactions or the recoil from asymmetric supernova explosions. In September 2025, astronomers reported detecting a rogue black hole displaced nearly a kiloparsec, more than 3,000 light-years, from the center of a dwarf galaxy, actively consuming material despite its isolation. These wanderers drift through the galaxy, invisible until something crosses their path. There might be millions of such isolated black holes in the Milky Way, silently warping space-time as they pass through otherwise empty regions. They pose no threat to Earth. Space is vast, and the probability of encountering one is vanishingly small. Black holes might not be the ultimate endpoint of gravitational collapse. Some theoretical models suggest that under certain conditions, quantum effects might prevent the formation of a true singularity. Instead, creating something called a gravistar or black star, an object that appears nearly identical to a black hole from the outside, but lacks a true event horizon and singularity. Other proposals include fuzzballs from string theory, where the black hole's interior is replaced by a dense tangle of strings. These alternatives remain speculative, but they address some of the paradoxes that arise when combining quantum mechanics with general relativity. Distinguishing between these possibilities would require observations sensitive to differences near the event horizon, perhaps through precise gravitational wave measurements. The nearest known black hole to Earth is Gaia BH1, located about 1,500 light-years away, relatively close by cosmic standards, but still far beyond our reach with current technology. It orbits a sun-like star, and the system is only detectable because of the star's wobble caused by the black hole's gravity. The black hole itself weighs about 10 times the mass of the Sun. Its proximity makes it an excellent target for detailed study, though still too far to reveal much detail about the black hole itself. In our own solar system, no black holes exist, and that's fortunate for life on Earth. A black hole anywhere near our Sun would dramatically disrupt planetary orbits, making stable conditions for life impossible. Scientists use black holes as natural laboratories to test the limits of physics. The extreme conditions near black holes, intense gravity, high temperatures, strong magnetic fields, and matter moving near light speed, cannot be recreated in any Earth-based laboratory. By observing black holes, astronomers can test predictions about how matter and energy behave under these extreme conditions. Every observation that matches predictions strengthens our confidence in theories like general relativity. Any observation that doesn't match could point toward new physics. So far, Einstein's century-old theory has passed every test, but scientists continue searching for places where it might break down, knowing that such breaks would be windows into deeper truths. When two galaxies collide and merge, their central supermassive black holes also eventually merge. Though this process takes millions of years, the black holes first spiral toward each other, losing energy through gravitational radiation. As they draw closer, they enter a phase called the final parsec problem, where the mechanism for losing the last bit of orbital energy becomes unclear. Recent observations of galaxies with dual black holes at various stages of merging help astronomers understand this process. The gravitational waves from the final merger of supermassive black holes will be detectable by the future LIS, a mission, opening a new window on these cosmic events. Each merger creates ripples in spacetime that carry information about the colliding black holes across the universe. The concept of a black hole has permeated culture as well as science. They've become metaphors for mystery, danger, and the unknown. In science fiction, black holes often appear as shortcuts through space or portals to other dimensions. While such ideas make for entertaining stories, the real physics of black holes is even more fascinating. Real black holes are both simpler and stranger than fiction usually portrays. Simpler because they're just space-time warped by mass. Stranger because this warping produces effects no human could have imagined before Einstein. The gap between popular conception and scientific understanding highlights the challenge of communicating abstract physics concepts through everyday language and experience. Some black holes seem to be spinning at the maximum possible rate, called the extremal limit. At this limit, the event horizon and inner horizon of the black hole merge, and the properties of spacetime near the black hole become especially strange. Spinning black holes drag spacetime around with them, creating a region where space itself is pulled along like water swirling down a drain. For an extremal black hole, this dragging effect becomes so strong that the geometry near the horizon takes on special mathematical properties. Whether truly extremal black holes can exist in nature remains an open question. Most observed black holes spin fast, but not quite at the maximum rate. Understanding what limits black hole spin helps physicists understand the fundamental nature of these objects. The material swirling around a black hole forms a structure called an accretion disk. Friction within the disk heats it to millions of degrees, causing it to glow brightly across multiple wavelengths of light. The inner edge of the disk can come very close to the event horizon. For a rapidly spinning black hole, it might extend down nearly to the horizon itself. The shape and properties of the accretion disk depend on how much material is available and how quickly it falls inward. Thin, geometrically flat disks form when feeding is relatively gentle, while thick, puffy disks can form during rapid accretion. The magnetic fields threading through these disks play crucial roles in channeling material inward and launching jets outward. Studying accretion disks teaches us about magnetohydrodynamics, the complex interplay of magnetic fields and moving plasma. In 2021, astronomers confirmed the existence of a triple system containing a black hole. Unlike binary systems with two objects, this system has a black hole orbited by two stars. The black hole, designated V404 Cygni, is about 9 times the Sun's mass, while its two stellar companions orbit at different distances. The discovery of triple systems has important implications for understanding how black holes form. If black holes only formed from direct stellar collapse, triple systems would be rare. The supernova explosion should disrupt the system. The existence of triples suggests that at least some black holes might form through direct collapse of gas clouds, without a violent supernova. Each unusual system we discover expands our understanding of the variety of ways black holes come into being. Light can orbit a black hole, just like a planet orbits a star, though the orbits are unstable. At precisely 1.5 times the Schwarzschild radius, the size of the event horizon for a non-spinning black hole. Light follows circular paths. This creates what's called the photon sphere. Light orbiting here is unstable. The slightest perturbation sends it either spiraling into the black hole or escaping to infinity. When we look at a black hole, photons from the photon sphere contribute to the bright ring we see. Some photons might orbit once, twice, or even many times before either escaping or falling in, creating concentric rings of increasingly faint images. In theory, infinitely many such rings exist, though only the first few are bright enough to detect. The mass of a black hole can be measured through several methods. For black holes in binary systems, observing the orbit of the companion star reveals the black hole's mass through Newton's laws of gravity. For supermassive black holes, measuring the speeds of stars orbiting nearby or the velocities of gas in the accretion disk provides mass estimates. Gravitational wave signals from merging black holes carry detailed information about the masses, spins, and distances of the merging objects. The size of a black hole's shadow is proportional to its mass, so direct imaging can also constrain mass. All these methods require careful analysis and sophisticated modeling, but they consistently reveal that black holes span an enormous range of masses, from a few times the Sun's mass to tens of billions of solar masses. Some galaxies harbor pairs of supermassive black holes that will eventually merge. The merger of supermassive black holes is one of the most energetic events in the universe, releasing more energy in gravitational waves than all the stars in the visible universe emit in light during the same time. Despite this enormous energy release, the merger itself might not produce much visible light if insufficient gas is present to fuel a bright accretion disk. This is why gravitational wave detection is so important. It allows us to see these events that might otherwise be invisible to traditional telescopes. The LIS, a mission, will specialize in detecting gravitational waves from supermassive black hole mergers, potentially observing hundreds of such events across the universe. Black holes might be connected to some of the most powerful phenomena in the universe. Gamma-ray bursts are brief flashes of high-energy gamma rays that occasionally appear from distant galaxies. The most powerful ones might originate when massive stars collapse directly into black holes, creating a brief but incredibly intense jet. These events shine so intensely that for a brief moment, their light can be brighter than entire galaxies. Though they happen far away, their glow reaching us as ancient echoes across space. Other gamma-ray bursts might come from the merger of neutron stars or a neutron star and black hole. Fortunately, they're rare and usually occur in distant galaxies. Understanding the connection between black holes and gamma-ray bursts helps astronomers trace the deaths of the most massive stars and the violent lives of compact objects. The mathematical description of black holes is surprisingly simple. A black hole in isolation is completely described by just three numbers: its mass, spin, and electric charge. This is known as the no-hair theorem. Black holes have no other distinguishing features or hair. All other information about what fell in is lost. This remarkable simplicity means that two black holes with the same mass, spin, and charge are completely indistinguishable, regardless of whether they formed from stars, gas clouds, or anything else. The simplicity is both beautiful and puzzling, especially given the information paradox it creates. Why should nature allow such elegant objects that seem to destroy information? This question continues to drive theoretical research at the intersection of quantum mechanics and gravity. Temperature and entropy have precise meanings for black holes, even though they initially seem like contradictory concepts. Black holes have temperature inversely proportional to their mass. Larger black holes are colder, smaller ones hotter. They also have entropy proportional to their surface area, not their volume. This area law of entropy was surprising when first discovered, suggesting deep connections between gravity and thermodynamics. The holographic principle, which emerged from studying black hole entropy, proposes that all the information in a volume of space can be encoded on its boundary surface. This radical idea has influenced theoretical physics far beyond black holes, suggesting that our three-dimensional reality might be a projection of information stored on a two-dimensional surface, like a hologram. Black holes can affect entire galaxy clusters. The most massive galaxies often sit at the centers of galaxy clusters, and their central supermassive black holes can heat the surrounding gas to temperatures of tens of millions of degrees. This heating prevents the gas from cooling and forming new stars, regulating star formation across the entire cluster. Jets from the central black hole can carve cavities in the surrounding hot gas, creating bubbles visible in X-ray images. These processes connect the smallest scales, near the black hole's event horizon, to the largest scales of galaxy clusters, spanning millions of light years. Understanding this feedback between black holes and their environments is crucial for understanding how galaxies evolve over cosmic time. Quantum mechanics predicts that even empty space isn't truly empty, but filled with virtual particles constantly appearing and disappearing near a black hole's event horizon. These virtual particle pairs can be separated, with one particle falling into the black hole while the other escapes. This is the origin of Hawking radiation. The escaping particle appears real, carrying away energy and causing the black hole to slowly lose mass over immense timescales, far longer than the current age of the universe for stellar and supermassive black holes. This process would cause black holes to evaporate completely. The final moments of a black hole's evaporation would be explosive, releasing the remaining mass as a burst of particles. This connects the physics of the very large, black holes, with the very small, quantum mechanics, in a profound way. Recent research has explored whether black holes could be detected through unconventional methods. In May 2024, scientists proposed looking for gamma-ray signatures from black hole morsels, tiny black holes potentially created during large black hole mergers. These morsels, with masses comparable to asteroids, would emit detectable Hawking radiation at gamma-ray energies. Another approach, developed in 2025, suggests watching for transiting primordial black holes through their positron emissions as they pass through our solar system. These creative detection strategies show how scientists combine theory, simulation, and observational capabilities to explore new ways of finding and studying black holes, especially ones too small or distant to detect through conventional means. The relationship between black holes and the fabric of spacetime itself is still being explored. General relativity describes gravity not as a force, but as curvature of spacetime. Mass tells spacetime how to curve, and curved spacetime tells mass how to move. Black holes represent the most extreme curvature possible, where spacetime becomes so warped that it closes in on itself. Some physicists wonder whether spacetime itself might be made of something more fundamental, perhaps emerging from quantum entanglement or other quantum properties. If so, black holes might be windows into this deeper level of reality. The quest to understand quantum gravity, how quantum mechanics and general relativity merge at the smallest scales, continues to drive theoretical physics research worldwide. Astronomers have observed phenomena that challenge our understanding of black holes. In November 2024, gravitational wave detectors observed black hole mergers, where the black holes had unusual spins. Some were spinning rapidly. Others had spins opposite to their orbital motion, both unusual and suggesting these might be second-generation black holes, formed from previous mergers rather than directly from stellar collapse. These observations show that the population of black holes is more diverse than simple models predicted. Dense environments like globular clusters might host many black holes that merge multiple times, building up mass through successive generations. Each unexpected observation prompts theorists to develop more sophisticated models of how black holes form and evolve. The future of black hole astronomy includes ambitious plans. The next generation, Event Horizon Telescope, aims to add more radio telescopes to the array and observe at multiple frequencies simultaneously, potentially creating the first movies of matter orbiting black holes. Other projects plan to observe black holes in polarized light across multiple wavelengths, revealing the magnetic field structures in detail. Space-based interferometers might someday achieve even higher resolution than Earth-based arrays. Each improvement brings us closer to understanding the dynamics near the event horizon, how matter falls in, how jets launch, how magnetic fields evolve. These observations will test general relativity in its strongest regime and might reveal hints of quantum gravitational effects. Black holes can merge with extraordinary consequences. When two supermassive black holes merge, the resulting black hole can receive a kick from asymmetric gravitational wave emission, potentially reaching speeds of thousands of kilometers per second. This kick can send the merged black hole wandering away from the galaxy center, or even eject it from the galaxy entirely. In some cases, the kick might be oriented nearly perpendicular to the galaxy's plane, sending the black hole plunging through the disk of stars and gas. Such events would be spectacular, though rare. Finding black holes that have clearly been displaced from galaxy centers would provide evidence for these kicks and help us understand the complex dynamics of black hole mergers. The study of black holes has practical applications beyond pure science. GPS. Satellites must account for relativistic effects, both the time dilation from their orbital speed and from Earth's gravitational field, to maintain accurate positions. These are the same effects that become extreme near black holes. Understanding how gravity affects time has enabled technologies that modern society depends upon. More speculatively, some scientists have proposed that advanced civilizations might use black holes as ultimate power sources or data storage devices. While such ideas remain far beyond our current capabilities, they illustrate how understanding extreme physics might enable future technologies we can barely imagine today. Observations of distant quasars, supermassive black holes actively feeding in the early universe, reveal that these objects grew to enormous sizes remarkably quickly. Quasars with billions of solar masses existed when the universe was less than 1 billion years old, only a fraction of its current age. How black holes grew so massive so quickly remains puzzling. Recent observations of black holes feeding well above theoretical limits, like LID 568, might provide clues. Perhaps black holes in the early universe commonly experienced brief episodes of super-Eddington accretion, growing rapidly during these bursts. Alternatively, black holes might have started from more massive seeds than previously thought. Solving this puzzle requires combining observations across cosmic time with theoretical models of black hole growth. Black hole binaries, two black holes orbiting each other, have been detected through gravitational waves from dozens of mergers. Each detection provides measurements of the black hole's masses and spins, building up a statistical picture of the black hole population. Recent detections have revealed black holes with masses in ranges once thought unlikely, including intermediate mass black holes, filling the gap between stellar and supermassive varieties. The distribution of black hole masses and spins tells us about how stars live and die, how black holes form, and how they find partners and merge. As detectors become more sensitive, they'll detect mergers from earlier in cosmic history, tracing black hole evolution across billions of years. Stephen Hawking once proposed that black holes aren't as black as once thought, and this insight has reverberated through physics for 5 decades. In September 2025, scientists reported new confirmation of Hawking's area theorem using gravitational wave data, the first direct observational test of this fundamental prediction. The theorem states that the total area of black hole event horizons never decreases, similar to how entropy never decreases in thermodynamics. Every merger detection provides a new opportunity to test this theorem by comparing the horizon's areas before and after merging. So far, observations match predictions perfectly, but scientists continue testing, knowing that any deviation would signal new physics beyond Einstein's relativity. Each test is both a tribute to Hawking's insights and a search for the limits of our current understanding. You might be feeling tired now. That's perfectly fine. Breathe slowly. Feel the cycles. Spacecraft orbit Earth. Earth orbits the Sun. The Sun orbits the center of the Milky Way. All are circles, cycles, endless orbits. Like your breath. Inhale, exhale, inhale, exhale. A small cycle within the vast universe. You are also part of that eternal movement. You don't need to hold on to anything. Let everything unfold in its perfect order, like planets silently rotating in their orbits. Unhurried, unresisting, simply existing. We're almost there now. Black holes remind us that the universe contains mysteries we may never fully understand. The singularity at their centers represents a boundary of knowledge, a place where our best theories break down and new physics must emerge. Yet, this unknown doesn't make black holes less real or less important. They shape galaxies, forge heavy elements, to generate gravitational waves, and test the limits of our most fundamental theories. In seeking to understand black holes, we're really seeking to understand the universe itself, how it began, how it works, and perhaps how it will end. Every black hole started somewhere. Stellar black holes began as massive stars burning brightly in some ancient sky. Supermassive black holes grew from smaller seeds, accumulating mass over billions of years through countless encounters. Even primordial black holes, if they exist, formed from quantum fluctuations in the earliest moments of cosmic time. Each black hole carries a history, though that history is hidden behind the event horizon. All we see now is the aftermath, the curved space-time, the orbiting matter, the occasional flash when something falls too close. The dark center in black hole images looks empty, but it isn't truly empty space. It's a region where space-time is so warped that all paths lead inward. Light trying to escape is pulled back, creating darkness, not from absence, but from inescapability. This darkness is different from the darkness of an empty room or the darkness between stars. It's the darkness of profound gravity, where space and time exchange their usual roles and all futures lead toward the singularity. Magnetic fields thread through the space around black holes, invisible lines of force that channel and accelerate material. These fields can store enormous amounts of energy, then release it in jets that span thousands of light years. The precise mechanisms remain under study. How does the field twist? How does it tap into the black hole's rotational energy? Each new observation adds detail to our picture. The magnetic fields reveal that even around objects as simple as black holes, complexity emerges in the interactions between matter, energy, and gravity. Time near a black hole becomes almost a tangible thing, something that stretches, compresses, and varies from place to place. Two observers at different distances measure time passing at different rates, yet each feels their own time flowing normally. This reveals that time isn't the absolute, universal flow we experience in everyday life. It's relative, flexible, intertwined with space itself. Black holes demonstrate this truth most dramatically, showing that time is woven into the very fabric of reality. The Event Horizon Telescope required cooperation between hundreds of scientists across continents. No single nation or institution could have captured those historic images alone. This international collaboration reflects how modern science works, pooling expertise, sharing data, building on each other's work toward common goals. The black hole images stand as monuments not just to physics and astronomy, but to what humans can achieve when we work together toward understanding rather than conflict. When matter falls into a black hole, it doesn't vanish. It becomes part of the black hole itself, slightly increasing its mass and size. The event horizon grows with each addition. In a sense, nothing is truly destroyed. It's transformed into a new form, woven into the black hole's space-time. The total energy remains conserved, just redistributed. This perspective offers a gentler view of black holes, not as cosmic destroyers, but as cosmic transformers, changing what falls into a new configuration of curved space-time. Light from black holes travels across the universe for billions of years before reaching our telescopes. The black hole images show these objects not as they are now, but as they were in the distant past. M87's black hole appears as it was 55 million years ago, when dinosaurs still walked on Earth. Sagittarius, a star, appears as it was 26,000 years ago, during the last ice age. We look not just across space when we observe black holes, but backward through time, witnessing ancient light that began its journey long before we existed. Some physicists wonder if our universe itself might exist inside a black hole. The mathematics allows for this possibility. A black hole interior might contain an entire universe expanding within, disconnected from the outside. If true, We might live in an infinite nested hierarchy of universes within black holes within universes. This remains highly speculative, more philosophy than physics, given our inability to test it. Yet, it illustrates how black holes push us to question even our most basic assumptions about reality and our place within it. The universe contains far more black holes than we've directly detected. Most are isolated and quiet, revealing themselves only if they happen to have a companion star that gives away their presence through its wobbling motion. The Milky Way might harbor millions of stellar mass black holes scattered throughout the galaxy. Supermassive black holes sit at the centers of most large galaxies, perhaps all of them. Together, these unseen black holes make up a significant fraction of the universe's mass, silently shaping galactic evolution through their gravity. Gravitational waves carry information across the universe that no other signal can convey. Light can be blocked by dust or absorbed by matter, but gravitational waves pass through everything almost unimpeded. They provide a clear view of black hole mergers, even when those mergers happen in regions too dusty or distant for traditional telescopes to observe. This makes gravitational wave astronomy complementary to traditional astronomy. Together, they provide a more complete picture of cosmic events than either could alone. Black holes exist at many scales, from hypothetical microscopic ones to supermassive giants, spanning more than 30 orders of magnitude in mass. This enormous range suggests that gravity's tendency to create black holes is universal. Give it enough density in a small enough region, and a black hole forms regardless of the absolute scale. The same mathematics describes them all, from the smallest to the largest. This universality is beautiful. One set of equations explaining objects across such a vast range. The shadows of black holes encode information about fundamental physics. Their exact size and shape depend on the properties of gravity itself. If gravity deviated from Einstein's predictions near the event horizon, the shadows would look slightly different. So far, observations match relativities, predictions within measurement uncertainties. But as observations improve, we might detect subtle deviations that would point toward quantum gravity effects or other modifications to our understanding. Each measurement tests not just the black hole, but the nature of space-time itself. Confronting black holes requires humility. For all our scientific progress, these objects mark boundaries of knowledge. What happens at the singularity? How is information preserved? What quantum gravity theory correctly describes the Planck scale physics near the center? We don't know yet. This not knowing is okay. It's part of the scientific journey. Every answered question reveals new questions deeper still. Black holes assure us that mysteries remain, that the universe still holds secrets waiting for future generations to uncover. The brightest quasar ever discovered shines from 12 billion light-years away, powered by a supermassive black hole, consuming a sun's mass of material every single day. This incredible feeding rate produces light so intense that the quasar outshines trillions of stars. Yet despite this fury, the light we see is ancient. The black hole appears as it was in the early universe. That distant black hole might be quiet now, or grown even larger, or merged with another. We see only its past, a reminder that all astronomy is archaeology, studying ancient light from long-ago events. Accreting black holes can become some of the most efficient engines in nature, converting up to about 40% of infalling matter's mass directly into energy, far more efficient than nuclear fusion in stars. which converts less than 1% of mass to energy. This energy emerges as radiation and jets rather than the black hole itself growing. The process demonstrates how gravity, in its most extreme form, can tap into matter's rest energy in ways that ordinary stars cannot approach. When the first gravitational wave was detected in 2015, it opened a new sense for observing the universe. For centuries, astronomy relied on light, from radio waves through visible light to gamma rays, all forms of electromagnetic radiation. Gravitational waves are entirely different, ripples in space-time itself. Detecting them is like gaining the sense of hearing after only having sight. Black hole mergers become audible through their gravitational wave signatures. This multi-messenger astronomy, combining light, gravitational waves, and sometimes neutrinos, provides richer understanding than any single messenger could give. The paradoxes of black holes, information loss, the firewall problem, quantum effects at the horizon, drive much of theoretical physics today. Resolving these paradoxes likely requires a complete theory of quantum gravity, something physicists have sought for decades. String theory, loop quantum gravity, and other approaches offer different frameworks, each with mathematical beauty and challenges. Black holes serve as testing grounds for these theories, places where quantum effects and gravity both become essential. The solutions, when they come, will likely revolutionize our understanding of reality at its most fundamental level. Black holes connect to thermodynamics in unexpected ways. They have temperature, entropy, and even emit thermal radiation. This connection suggests deep relationships between gravity, quantum mechanics, and information theory. The holographic principle, that a volume of space might be described by information encoded on its boundary, emerged from studying black hole entropy. These connections hint that our three-dimensional world might emerge from something more fundamental, perhaps information itself. Black holes, once thought simple, turn out to be keys to profound questions about the nature of reality. Intermediate mass black holes remain elusive, with only a handful of candidates confirmed. These objects, too massive to form from single stars, but too small to be supermassive, might form through multiple mergers in dense star clusters. Finding more of them would complete the picture of black hole formation and growth. Recent observations in May 2025 provided evidence for several such intermediate mass candidates, slowly filling in this mysterious gap. Each discovery helps trace the path from stellar black holes to the supermassive giants, revealing how gravity builds complexity over cosmic time. Some black holes have been observed to suddenly wake up after long periods of dormancy, beginning to feed again after years or centuries of quiet. The triggers for these awakenings vary. Sometimes a star wanders too close. Sometimes gas from a galactic collision funnels toward the center. These episodes can be brief or last for thousands of years. Sagittarius, A star, our galaxy's central black hole, is relatively quiet now, but has awakened in the past and may awaken again. We see the universe at one moment in time, a single frame from a billion-year movie. Laboratory experiments can now simulate some aspects of black holes. In quantum simulations, using chains of atoms or optical systems, scientists create analog event horizons and observe phenomena like Hawking radiation in controlled settings. These experiments don't create actual gravitational black holes, but they demonstrate that the physics Hawking predicted should occur near any horizon-like structure. Such analogues help verify theoretical predictions and explore aspects of black hole physics that can't be tested with astrophysical black holes. They bridge theory and experiment in clever ways. Black holes might help explain cosmic inflation, the rapid expansion of the early universe. Some theories propose that the universe itself emerged from something like a black hole in a higher dimensional space. While highly speculative, such ideas show how black hole physics connects to cosmology, quantum field theory, and the earliest moments of existence. Every mystery we solve reveals connections to other mysteries, weaving together seemingly disparate areas of physics into a more unified understanding of how nature works. Studying black holes means looking both outward and inward simultaneously. Outward to the largest structures and most extreme environments in the cosmos, inward to the deepest questions about space, time, information, and reality. Black holes are both astrophysical objects and theoretical laboratories. They challenge us scientifically while inspiring wonder. They remind us that the universe is both comprehensible, following mathematical laws we can discover, and mysterious, containing phenomena that still defy complete understanding. This balance between knowing and not knowing drives science forward. Black holes will exist long after stars stop forming, after galaxies dim, perhaps until the very end of the universe. As they slowly evaporate through Hawking radiation over unimaginably long timescales, they may be among the last structures to disappear. In this way, black holes bookend cosmic history, forming from the deaths of early stars and persisting into the deep future when the universe grows cold and dark. They are both endings and beginnings, both simple and complex, both understood and mysterious. In studying them, we study the universe's past and its possible futures, connecting the largest questions about space and time to the smallest scales where quantum effects reign. And so, our quiet journey through the mysteries of black holes comes to a gentle close. We've traveled from the bright quasars consuming suns in distant galaxies to the sleeping giants drifting silently through our own Milky Way, discovering along the way that even in darkness, there is beauty and understanding. From the first theories penciled on paper to images captured by Earth-sized telescopes, we've glimpsed how black holes are both endpoints and beginnings, places where matter transforms and space-time bends in ways that still inspire wonder. Black holes remind us that the universe contains mysteries worth contemplating. Much of what is most profound happens in silence. Gravity, warping space-time, information, perhaps preserved in ways we don't yet understand, time flowing at different rates depending on where you stand. They teach us patience in seeking answers, humility in accepting what we don't know, and curiosity in pursuing what might yet be discovered. By pausing to notice these cosmic mysteries, we glimpse the extraordinary woven throughout the ordinary darkness of space. And now, in these final minutes, take the deepest breath you can, as deep as possible. Think about unity of every atom, every event, every moment in the universe. You are not separate. You are a link in the endless chain. Think about the unity of every atom in a black hole, where all boundaries dissolve. Light, matter, time, all becoming one. You too can dissolve into sleep like that. No boundaries left between you and rest. Let your entire being dissolve into the gentle darkness, into the soft gravity pulling you into sleep. Prepare for deep sleep. No boundaries left, only peace. If this gentle journey through the cosmos brought you peace tonight, perhaps share it softly with someone else who's searching for stillness under the stars. It might be exactly what another restless mind needs to finally let go and drift. One quiet share, one peaceful night at a time. But there's no need to do anything now. Nothing at all. You've traveled far tonight, farther than most journeys take you. You can allow these thoughts of black holes and mysteries to fade now, like stars dimming at dawn, leaving only the peaceful calm behind. Let your breathing deepen. Let your body feel heavier, as if gravity itself is gently pulling you down into rest, into safety, into the embrace of sleep. If sleep comes, let it carry you like matter, crossing an event horizon, smoothly, inevitably, into a realm where time and weight no longer matter. If your eyes are still open, the next video is waiting for you, ready to continue the journey. But if they're closed, stay there. Stay in the darkness that feels safe and warm. Tomorrow, black holes will still be spinning in distant galaxies. Stars will still be orbiting at the centers of their galaxies. The universe will still be expanding, mysterious, beautiful. But tonight belongs to stillness. Rest well, gentle explorer, and remember, even in the deepest darkness of space, there are wonders waiting to be understood, mysteries that connect us all to the cosmos we call home. Dream deeper with bedtime science.